an infinitely long cylindrical conductor, and there is a cylindrical hole, that is a cylindrical cavity, and the axis of the cylindrical cavity is parallel to the axis of the full cylinder. And a current flows along the length of this cylinder, let's say in that direction, and the current is I. Now let's take a look at the cross section of this cylinder. Here is the cross section of the cylinder. So let's say the radius of the full cylinder is R, and let's say the radius of this cylindrical cavity, let's call it A. And the center, that is the axis of the full cylinder, is out here, and the axis of the cavity is here. Now the current I is uniformly spread out in this area. So the current density, which is given by J, is going to be the current flowing through the cylinder divided by this cross-section area, because current density is current per unit area. So that's going to be pi r squared minus pi a squared. So let us assume J is calculated. But J is a vector. Current density is always a vector, and the direction of this current density is the direction in which the current is flowing. So in this diagram, the current is flowing out of the page. So question is, what is the magnetic field at some point inside this cylindrical cavity? So what we are going to do is very simple. We are going to start with the full cylinder, find the magnetic field at a distance small r from the center, that is from the axis, and from that we are going to subtract the field due to the cavity. That is the field due to a small cylinder. Once we subtract it, we get the field due to the cylinder with the cavity. This is what we usually do. But before we do that, let's find what is the magnetic field at any point inside a cylinder carrying current spread uniformly across its cross section. So this is the cross section of a current carrying cylinder. So let us say we wish to find the magnetic field at a distance small r from the axis of this cylinder. So we want to find the magnetic field at this point, described by the position vector r from the axis. To that end, what we are going to do is we are going to draw an Amperian loop. So let's do that. Let's draw an Amperian loop like so. And we know that the magnetic field is tangential to the Amperian loop. Everywhere around the Amperian loop, the magnetic field is tangential. So now let's apply Ampere's law around this loop. So Ampere's law is integral B dot dl around the closed loop is going to be equal to mu 0 times the current enclosed. So integral B dot dl simply becomes B times 2 pi r, and that is equal to mu 0 times the current enclosed. The current enclosed is the current flowing through this area, and that's going to be J times pi r squared. So pi cancels and 1 r cancels. That gives us the magnitude of the B field as mu 0 by 2 J r. Can we write this B field as a vector? Now take a look at this vector. We can see the direction. This is the B field, and the current density is coming out of the page. So if you consider J, which is coming out of the page, J cross R. So use your right hand and fold J into R. You will find that the direction is the direction of the magnetic field. And J and R are perpendicular to each other because R lies in the plane of the page and J is perpendicular to it. So J cross R is simply JR, and the direction is B. So this can be written as mu naught by 2 J cross R. So now let's go back to our cylinder with the cavity. So we wish to find the magnetic field at a point like this. So let's call this position vector from the axis of the full cylinder. Let's call that R1. And so that vector is R1 vector to the point where we want the magnetic field. And let's find the position vector from the axis of the cavity. From the axis of the cavity, let's call this vector R2. Now the magnetic field at this point, due to the current flowing through the full cylinder, that is through this area, minus the current flowing through this area, will give us the magnetic field at that point. So let's do that. So it's going to be mu naught by 2. J is the same for both. So J cross R1 minus mu naught by 2 J cross R2. This is R2. So the cross product is distributive over addition and subtraction. So we can take mu naught by 2 times J outside cross. You have to be careful with the order. So it's R1 minus R2. But take a look. This is R1 and this is minus R2. So R1 minus R2 is going to be this vector from the axis of the full cylinder to the axis of the cavity. Let's call it D. So the magnetic field is mu naught by 2 J cross D. And interestingly, it is independent of this point inside the cavity. Everywhere inside the cavity, it's a uniform magnetic field. And what's the direction? Remember, J is coming out of the page. If you do J cross D, you can convince yourself that the magnetic field is going to be in this direction. So inside the cavity, it is uniform and points in that direction. That's it for this problem. Thank you.